Hi, so as you can see, obviously Avi couldn't join us today, so I have the pleasure to host the last ITC Luncheon of the academic year. And I also have to say that the gavel thing was in my bucket list, so I can basically retire. So before we start, I have a few final announcements for the last ITC Luncheon of the academic year, and we wanted to thank all the people that helped organizing all the ITC colloquia and also the ITC Luncheon. In particular for the ITC Colloquium, Vadim Semenov and Kaylee Brower. For the ITC Luncheon, Scott Lucchini and Yu Ying Mi. And of course all the ITC administrators that helped organizing everything. So TJ Martin, Uma Mirani and Jacqueline Donahu. And also of course the facilities team to help with set up, cleaning up and everything to make this work. So Jared, Joel, Bob and Jesus. And of course also Eric Quito for funding the ITC Luncheon, so we want to make a round of applause for So thank you for making all this happen for the academic year. And we have a great lineup of speakers today. We have Suchitra Narayanan from the CFA and also the Institute for Astronomy in Hawaii, and also Anirudh Patel from Columbia, McGeoch also from the CFA, and to conclude, Scott Lucchini from the CFA. So without further ado, let's start from Suchi Narayanan, we're going to talk about organosulfur chemistry in the birthplaces of stars and planets.
Can everyone hear me? Okay, so hi everyone. I'm Suchi Narayanan, and I've conducted majority of my thesis work here at the CFA in the Oberg lab. I also have some computational chemistry, so the C of ITC. And without further ado, I'll talk to you about some of my thesis work. So I first wanted to highlight why we care about sulfur in the first place. Of course, it's one of the 6 elements that we know that is necessary for life as we know it. But it's also essential to kickstart the origins of life chemistry that we require in order to look at life as, prebiotic life as we know it. And so there's a huge problem where we can't account for about 95% of the cosmic sulfur budget. And this is because of something called the missing sulfur problem that we've known since the 1990s, which forms the basis of my thesis. How can we understand sulfur if it's so hard to observe? Well, theoretical modelers leverage the periodic table, specifically oxygen with respect to sulfur. And the reason that we care about oxygen is because same group elements are isoelectronic. They have the same number of valence electrons. And if we go back to high school chemistry, valence electrons are responsible for an element's reactivity. And so there's this assumption, which is we can infer how sulfur-bearing organics form using their oxygen analogs. The most updated gas-green reaction network predicts that most of the missing sulfur can be locked up in organosulfur ices, and it's based on this assumption that S and O chemistry proceeds similarly. So when I say organosulfurs, it's a sulfur compound containing a CH bond, and the one I'll talk to you about today is the simplest complex organosulfur, methyl mercaptan. And I do every experiment with respect to its oxygen analog methanol, which is super well understood. There's a lot of agreement between theory, models, and theory, experiments, and observations. So everything that I do is relative to methyl mercaptan and methanol chemistry. It's been detected towards several sources, notably not disks. And so if we want to understand if organosulfurs can be this sulfur sink, we have to empirically characterize some of the fundamental astrochemical models, or fundamental astrochemical properties in order to see if they agree with our models. And so the fundamental question is, when is methyl mercaptan in its gas or ice phase? This is the first of several chapters of my thesis, but the one I'll focus on today. And so if we were to look at an edge-on disk, we know that molecules condense out as a function of radius or temperature. So as you go from closer in to outer, we know that we form what are known as snow lines. So the water snow line, then volatiles. But we know that ices are not necessarily pure. We have mixtures of H2O and other volatiles. So my lab mate has definitely given some of these ITC lunches and talked about entrapment, where we know that volatiles that we expect to be desorbing further out are actually desorbing much closer with water. So their snowline location shifts inwards. And this is pretty efficient, about 60% at its highest. And so we need to consider mixtures as well. How do we simulate disk conditions in the lab? Well, we have 4 in the Oberg Astrochem lab. If you haven't yet seen it, please message me and we'll give you a tour. But this is kind of difficult to look at, so I have some drawings that I'll go through to just show a brief experimental procedure. So we first have to get to low temperature and low pressure with our cryostat. We get down to 10 Kelvin, 10 to the minus 10 torr. For context, our atmosphere is 760, so very low pressure. We introduce our molecules through this gas line doser that's connected, which the gas line isn't shown here, but it feeds into this isolated substrate that's infrared inactive, and that's where we grow our ices. This is connected to just orient you guys, we're here outside in the cold part of the disk. This is connected to a heater that can actually induce sublimation, so that's basically moving inward and causing our ices to sublimate. We can also process it via radiation, which I won't talk about those experiments today, but we have a UV lamp, we have electron gun, atom bombardment lasers, so a bunch of ways to process the ice. The first data product is an infrared spectra, which characterizes the ice phase. The second one is a quadruple mass spectrometer, which allows you to characterize the gas phase. And this will be majority of the plots I'll show you today, so I wanted to orient you guys. As you're heating up the ice, your signature in the QMS will increase. If you integrate that, that gives you the total amount of species. But I want to point you to this part of the curve which allows us to probe the ice-gas boundary. So that's what we want to characterize if we want to figure out what's going on with the snow line. So this is the paper that I'll be talking about today. The different ice matrices that I'll be talking about will be pure, layered, and mixed, which all have different interactions. So if we were to just think of pure ices, that's just looking at how different molecules, I show methanol here, methyl mercaptan here, how they interact with respect to each other. But of course, water is the most abundant molecule in ices. So we want to see how this molecule interacts with water specifically. So we have a thick water ice and then less than 1 layer of methyl mercaptan. So you're truly probing that interaction. But of course, that's also not realistic. So then we go to our most complex one, which is a mixed ice, which is all particular interactions between water and a species. We also look at triple component ices with CO2. And note that all of these will have different desorption kinetics, which is just a fancy way to say how they sublimate, which is seen by the QMS. So the first of these curves of the pure ices is what I'll show right now, which is called a TPD curve. So just to orient you guys, this is the pure ice, comes off at 107 Kelvin, methyl mercaptan. This is part of the computational chemistry. I won't go into those details, but just to show you what interaction we're actually probing. Then you have methanol, which desorbs after, which is kind of expected. And all this just tells us is that methyl mercaptan is more volatile than methanol because it desorbs at a lower temperature. But of course, this isn't realistic. We have to look at layered ices. And so this is probing methyl mercaptan with water. And we have the water desorption curve over here. What's surprising is that it's coming off majority at its same temperature. And I want to highlight that this little bump, it kind of goes towards the last part of my talk, which is the entrapment, but it doesn't increase as we increase our submonolayer curves. And so I just want to emphasize that that's not truly binding that we discovered afterwards, but this bump is not necessarily any sort of methyl mercaptan water interaction. On the contrary, methanol hugs that water curve, and that's kind of expected because we know that it exhibits hydrogen bonding, and this is also clearly seen as you increase the submonolayer, like less than 1 layer of methanol on water, it increases, and that curve, that part that's hugging the trailing edge of the water curve, increases as well. And so qualitatively, we can just say that methyl mercaptan is indifferent to whether it binds to itself or water. Methanol interacts with water significantly, and our snow line for methyl mercaptan should be further out. But also, this isn't realistic. We have to think of our mixed ices. I don't go into details of how I got the binding energies. in the interest of time, but I just want to orient you guys. Methyl mercaptan is similar for both pure and water, and methanol is much higher, and we expect the methanol to water to be higher than that. And so if we were to look at entrapment, I just show a ternary ice with CO2 as well. We know that CO2 comes off here, methanol here. There's two curves for water desorption, the recrystallization, and it's what we call co-desorption. And I just want to emphasize what the recrystallization one tells us. This is known as volcano desorption, and it's when your water ice matrix restructures, so it shakes a little bit and allows for an abrupt release of molecules that are entrapped. And so for methanol, it comes off at all three. When we look at, and what we define as entrapped is what comes off after its pure desorption. And CO2 comes off at its pure, it comes off at all three as well. But methanol, or methyl mercaptan, basically only comes off at the volcano peak. And it's 100% entrapped, despite what I just told you and spent some time talking about, the fact that it doesn't bind to water. And something also interesting is that CO2 mostly comes off with methyl mercaptan as well. So this is really surprising. I ran several experiments looking at varying thicknesses, varying dilution, so relative ratios of components. And only in the volatile rich, which is the bottom over here, can we see some of the methyl mercaptan coming off at its pure. And so what I want to highlight is that we figured out that methyl mercaptan does not bind to water, but it's consistently 100% entrapped. And what we concluded, based on some of our computational chemistry as well, is that methyl mercaptan's size is inhibiting its ability to diffuse through the water matrix. Now I wanted to see how this affects larger molecules as well. And so what I did was methyl mercaptan, methanol, and water. And previously I showed you that methanol binds a lot to water. And what's surprising here is that methyl mercaptan's presence at even levels comparable to 67P, which is our most well-studied comment, is that methanol is desorbing only at the volcano. So not only is it making it 100% entrapped, but it's affecting its binding to water as well. And so this is the first time we've been able to constrain the pore size of a water matrix, which we've never been able to do before because it's super difficult to understand the structure of water ices. So this is a pretty cool way that we're able to see this size effect that affects sublimation. And so this difference is only 15%. And so the main result is that if we think that prebiotic molecules larger than methyl mercaptan form with water, we would expect them and other smaller volatiles to be available super close into the star than we would actually expect. And so the main conclusion from this is that we could be severely underestimating the inventory of volatiles close into the snow line, and this is important because this is where we think that planetesimal formation is pretty efficient. So very cool microphysics that has pretty large implications. Thank you.
Thank you, Sushi, for a great talk. We have time for questions. Yes.
Is the ratio of your sulfur-based methanol molecule, like the ratio between that with methanol and CO2 and water, representative of the ISM, or are you enhancing it, or yeah?
So this one is the 1 to 8 to 33 is the closest that we have to cometary abundances, which we expect to have preserved the solar nebula. And so they are realistic ratios. I also do this at very, very dilute ratios in thick ices and thin ices, which are the top. And that little peak at the end, that just over here, I don't know if this works. I don't know. The top one, 1 to 45 at 434, that secondary peak is just crack propagation. It's too thick of an ice to let all of it come off at once. If you were to look at the thicker version of methanol, there's continuous desorption at thicker ices, so we can actually tell that methyl mercaptan wants to escape, but it just can't because the pore sizes and cracks in the ice are not propagating quick enough. And so that was the reason we looked at very different ratios, also volatile rich and volatile depleted, and all of them show this effect. So we're pretty sure that it's the size that's inhibiting the diffusion.
All right, we have time for another question. Morgan, yeah.
This is really amazing. So can you imagine setting up an experiment where you take molecules of different sizes and see how porous the water is to that?
So
thing kind of thing?
that's actually
Imagining like fish of different sizes trying to get through a net.
Yeah, so that's the follow-up that I'm trying to do with this. I've looked at acetonitrile CH3CN, ethane, propane, so larger hydrocarbons as well. And we see this effect pretty well. And another thing that we also see is this effect with methyl mercaptan affecting the desorption of other ones. And we see, Karin wants me to call this champagne desorption, which if you can think of methyl mercaptan acting as a little cork to the pores, and the moment that it can escape, it's basically bringing everything else with it, because the whole thing with methanol not co-desorbing, it's inhibiting that. And so I've been doing follow-up experiments for this to basically validate this effect, and we do see it. I just don't have those plots right now. But yeah, it's really cool that we're able to really look at the ice, constrain what an interstellar ice structure can be.
Yeah.
All right, so let's thank Sushi. And now we move on to the second speaker of the day. We welcome Anirudh Patel, or Ani, from Colombia, who is going to talk about Magnetar giant flares, a new site for the R process.
A graduate student at Columbia, about halfway through my PhD. I'll be talking about some work with a great group of collaborators, including my advisor, Brian Metzger. I'm also a member of the theoretical astrophysics group at Columbia, and I'm part of the transients group at the Center for Computational Astrophysics at the Flatiron Institute. So so we'll be talking about how we found evidence for a new site, astrophysical origin for the heavy elements as they're synthesized through the rapid neutron capture process, and this site is Magnetar giant flares. So the R process is approximately responsible for producing half of the elements heavier than iron we see on the periodic table. So up to iron, you can produce them through nuclear fusion. The main kind of idea behind the R process is if you have an iron group nucleus, what we call a C nucleus produced through nuclear fusion, for example, you bombard it with a high flux of free neutrons. You can capture many of these neutrons, build up a very neutron-rich isotope of iron. Of course, you eventually get a beta decay. This will produce the next heaviest element, and this happens in rapid succession, producing the heavier and heavier neutron-rich nuclei. And this process releases energy. The beta decays release electrons, gamma rays, neutrinos, and that's we'll talk about how that manifests as observable properties in a second. So kind of the key thing here you need is a neutron-rich environment, right? So you need an electron fraction below 0.5. The lower electron fraction, the better. So, of course, we know that neutron star mergers, as of now, are the only confirmed site of the R process. We know that from the kilonova observation in 2017, right, which was widely interpreted to be powered by the radioactive decay of these R process nuclei freshly synthesized in a neutron-rich ejecta of the merger. There's several other sites, mostly having to do with core collapse supernovae. I won't go into the details, but kind of the key picture is that these sites have not yet been observationally confirmed. I'm going to try to convince you that the new picture, our new understanding of the R process, so it now looks something like this, where we have, sorry, okay, oh, there we go, it's backwards, no. Now we have observational evidence for Magnetar giant flares as a new site for the R process. This is based on some work we put out recently along with my collaborator Jakob Sehula. So magnetars are, of course, these highly magnetized neutron stars. Their high magnetic fields power a range of radiative outbursts, the most powerful of which are these giant flares. So you can kind of think of the mechanism behind these giant flares similar to solar flares. It's not perfectly understood, but some of the experts will tell you that's probably magnetic reconnection which drives these events. There have been 3 of these flares detected nearby, so in 1979 in the Large Mesh-London Cloud, 1998 and 2004 in our own galaxy. The most energetic of these flares was a 2004 event from SGR 180620, about 10 kiloparsecs away. This event released a total of 2 times 10 to the 46 first energy. Most of this energy was released in this prompt gamma ray spike, which if you were to look at it from a distance, for example, an extragalactic magnetar, it would look like a short GRB. And then you also get this characteristic X-ray tail, which basically has to do with the fact that this plasma, which is emitted during the flare, that produces this spike. Eventually, some of it is actually trapped when the magnetic field lines reclose. Of course, our neutron star is rotating, right? So this plasma is cooling in the trapped field lines, and it's co-rotating as it's cooling. So that produces this X-ray tail with modulations around 8 seconds, which is the spin period of this particular magnetar. There's also evidence for baryon ejection in these sites. So we have these radio afterglows. If you model kind of a synchrotron radio emission model that's produced by a forward shock, right, as you eject baryonic material from the surface of the magnetar, you can fit the observations quite well. From the modeling and observations, we can infer kind of the key properties of this baryonic ejection is that, that 10 to the minus 8, 10 to the minus 6 solar masses of material were ejected from the surface of the star at about 0.2 C. So the mechanism for baryon ejection that was proposed by our collaborator Jakob Sahula, also Brian Metzger, Todd Thompson, is that this magnetic reconnection event, which heats up the plasma in the magnetosphere, which produces the flare in the first place, it temporarily creates a high pressure shell right above the surface of the magnetar. This can drive a strong radiation dominated shock into the outer crust of the neutron star, compressing and heating up the material. Now, once this external pressure is relieved via the paraphoton outflow that produces the flare, your shock heated and compressed crust finds itself overpressurized with respect to its surroundings. So it begins to decompress, kind of like spring uncoiling. Now, a fraction of this material that has enough energy from the shock will actually become ejected and unbound from the system. And of course, if you have neutron-rich material that's ejected, much in the same way in the neutron star merger, that's kind of an ideal site for the R process. So we want to study this in a little bit more detail to calculate the synthesized abundances to determine the radiative signatures. So we can basically take Jakob's hydrodynamical simulations. We kind of develop a simplified analytic model from his simulations to calculate the key properties that we need for nucleosynthesis. So things like the entropy, temperature, which we can get from the shock time conditions of an equation state. The electron fraction, of course, is the key thing. How neutron rich is this ejecta? Now this has to do with how deep inside the neutron star you're excavating this material from, right? So the deeper you go, the more neutron rich you are. So for example, for 10 to the minus 6 solar masses of material, excavate spherically symmetrically, that corresponds to an electron fraction of about 0.40, which we take for our fiducial model. And the hydro simulations also give us, kind of show this homologous density profile with the bulk velocity being at about 0.1, 0.2 C. So these parameters enter our fiducial model. We put these things into a nuclear reaction network calculation to estimate the synthesized abundances. This is what we get. As you can see, we're able to get kind of a strong first peak R process here at 90, mass number 90, strong second peak at mass number 130, as well as a moderate abundance of heavy R process nuclei at mass number 200. So that's like gold and platinum. As I mentioned, these R process nuclei, when they're produced and as they decay, they release energy. So this is the total energy generation rate in the form of electrons, gamma rays, and neutrinos. It goes as a T to the minus 1.2 power law. So for the case of neutron star mergers, the number is T to the minus 1.3. The exact power law depends on the exact synthesized abundances. Our abundances are slightly different, hence the different power law. Now we basically have everything we need to put this in a light curve model, right? We have our radioactive energy source term. We have our composition of our ejecta, which tells us the opacity of the material. We put that in kind of a multi-zone semi-analytic kilonova light curve model, accounting for the separate thermalization efficiencies, electrons, gamma rays, neutrinos, of course, escape the system. Here I've shown our results for 3 different ejecta masses. You can kind of think of these as mini kilonovae. They have about 10,000 times less mass than your typical neutron star merger kilonova, and therefore 100 times shorter duration. We can also get the kind of estimate the photometric bands, light curves and photometric bands. So for example, in the near UV, this is what it looks like. This is basically just to show you that for extragalactic source distance, if we assume, albeit an optimistic slew time for an upcoming telescope like Ultrasat, this should be detectable. For a source in our own galaxy, 15 kiloparsecs, this should easily be detectable in the optical with ground-based instruments. So this is kind of what the picture looks like in that KV MEV range, right? So I mentioned you have your prompt spike, you have your X-ray tail, and now we're saying there's this third component, right? This is the radioactive ejecta. So it's not quite the complete picture yet because as this ejecta diffuses and becomes less dense, you might expect some of these gamma rays to actually escape unattenuated, right? So I mentioned some of these gamma rays kind of thermalize, they heat up the ejecta, produces optical UV signal, but eventually more and more gamma rays will escape unattenuated, powering a separate gamma ray signal that should be observable. So you can actually just do kind of a simple analytic estimate, right? You just take a ball of spherically expanding material, you calculate the time it becomes optically thin to gamma radiation, accounting for the opacity for photonization, confidence scattering. You find the peak time scale for an ejecta mass of 10 to the minus 6, moving at 0.1, 0.2 C, should be 700 seconds. We can send these, we sent these preliminary predictions to Eric Burns, who's an observer. We asked him if there were any previous constraints. Now it turns out there's a third component that was observed in the giant flare light curve in the MEV range. So here you have your prompt spike, right? That's the pair of photon outflow I talked about earlier that produces that is the characteristic signal of the flare itself. You have your decaying X-ray tail. We're using 50-second binlets here, so you can't see the oscillations. But around 400 seconds, you see there's this third component here that was detected by the integral satellite. We can take a closer look at the peak, and it turns out the peak is at 700 seconds. We can also fit the decay slope from the peak. Turns out to be t to the minus 1.2. So again, this is almost exactly consistent with what we were finding based on our simple estimates. So we can now take a closer look at the gamma ray light curve here. I'm not going to go into the details, but basically we just take our nuclear reaction network calculations, synthesize abundances, time-dependent abundances. We fold in nuclear level structure data to get the gamma ray emission. We calculate the total gamma ray energy generation rate, which turns out to be about 30% of the total radioactive heating rate. We put that into another semi-analytic light curve model, again accounting for opacities for gamma rays, which is confidence scattering for ionization. We find that our model is consistent with the data. So you can see here again, the peak is consistent, the slope is consistent. Third point here is that the total integrated flux is also consistent. So here we're not only using the light curve data from integral, but also combining that with data from RESI. And we also repeat the same thing with CONUS wind, find the same data point here, and our model matches that nicely. Now, kind of the final nail in the coffin here is the spectra. So here, this is the synthetic spectra we produced with our model. But of course, your ejecta is moving at 0.1, 0.2 C, so things are Doppler broadened. So when we account for Doppler broadening, it looks something like this. This also accounts for radiation transport effects, so again, photonization, confidence scattering. Now, it's quite remarkable when you plot the actual data taken by RESI on it, you find this. So the energy range that RESI was able to make measurements in is shaded in gray here. You can see the data fits quite well with our predictions. So now if you take this as evidence for our process in these sites, there's some implications of this. So if you just kind of take the rate of these 9 giant flares, average over the history of the galaxy, you assume that these energetic flares can produce about 10 to the minus 6 solar masses of our processing material each. You find that these flares can contribute between 1 and 10% of the R process in our galaxy. So while neutron star mergers are still a dominant site, the issue with mergers is that they have a delay time relative to star formation, right? So that's the metallicity here on the x-axis. So of course, increased metallicity corresponds to later in cosmic time. Europium is percent R process origin. So really, your europium to iron ratio relative to solar is a measure of your R process enrichment. So you can see here, we see stars early in galactic history that are enriched in R process elements. So these can't be explained by mergers because of the delay time. Magnetars are born relatively early in the galaxy, so they could very well explain, at least in part, this enrichment early in galactic history. So I'll just leave you with my summary slide. So again, just want to reiterate that if we take the mass and velocity constraints from the independent radio observations, we put that in our model, we're able to hit all 4 of the observational constraints for the MEV observables here. Thank you.
Thank you, Ani. We have time for questions. Yes.
I guess I'm wondering, with the rates being low, could they be responsible for all of the odd process of low metallicity, or do we still need another aspect?
I think the answer to that is uncertain. I think so we'd have to do some sort of galactic chemical evolution study compared to observations of metal poor stars to say for sure. In our simulations of these proto-neutron star winds that are highly magnetized or rapidly rotating, we do see you can get a robust R process. It's unsure if people can confirm that observationally because there's a lot of other stuff in supernova ejecta that could obscure the R process signal, but theoretically at least we know we can produce R processes in types of supernovae. So we don't know. There could be other sources out there that we just haven't discovered yet.
I'll actually ask you a very good question. One of your cartoons is implying that there is some sort of X-ray emission as well. Can you tell us a little bit more what's the peak emission and how long you expect it to be visible for Chandra, for example?
This part, or?
Like the X-ray tail that is there.
So the X-ray tail is a few hundred seconds. I mean, this has been observed for the last 2 galactic giant flares. I think also the first giant flare from the LMC. I think various instruments should be able to observe that. I don't recall off the top of my head. I mean, Integral was able to observe this component, for example, in the 2004 flare. So I think if you can get an X-ray instrument onto the flare quickly enough, you should be able to catch the tail. For a source that's inner galaxy, I think for extragalactic sources, you can't really see it because it's too dim. You can see the prompt gamma ray spike, and that's kind of the trouble with distinguishing extragalactic Magnetar giant flares from short GRBs, because you can't really see these other characteristic features of the flare compared to a normal short GRB.
Thanks. Any final quick questions? If not, let's thank Ani again. And now for our third speaker, we have Julie McGeoch from the CFA. And she will talk about how the Hemoglycin lattice fills space. You can just click on it.
Right, okay.
Here's your microphone.
Yeah, so this is
Got a pocket for that.
Hi, I'm Julie McGeoch from CFA, and I work on a polymer that I collect from Earth infall samples. And today I'm going to pose the proposition that the polymer that is called hemoglycin, and it forms a very low density lattice, is the biggest thing that can be formed by the least material in a molecular cloud. Now, the background is that the same polymer of amino acids, iron, and silicon has been found in carbonaceous meteorites, fossil and model stromatolites, and seafoam. And it has a standard length of 5 nanometers and forms the lattice in 3D space. And the present work is going to address why it's dominant in all the solar system sample studies. And the question is, does the hemoglycin's dominance come down to space-filling efficiency? So this is the basic molecule. The top shows the core unit. It is 2 antiparallel chains of glycine, and at the end, the green iron atoms are shown. Bottom right shows the structure we think the lattice adopts. And the left, I'll and amplify here. Now this image is when I purify the polymer in a chemistry two-phase system. It occupies an interface between a dense chloroform layer and a polar water layer. And the question is why this image suggests that hemoglycin has a low-density lattice topology. First point is the structure material via MALDI, which is a mass spectrometry technique, is always hemoglycin. The volume of the material floating at the interface in the extraction vial is as large as the initial sample, but that sample contains only up to 5% organic molecules. Therefore, it was a low-density lattice. It has definite angles, as you can see, of 120 degrees, which indicates a regular structure. And the theory at this point was that a single type of lattice formed. A regular lattice was seen in fiber X-ray diffraction, and the lattice rod length was 5 nanometers. The fiber crystals formed on dehydration in the interface layer. And the candidate lattice was sought. That had the highest space-filling efficiency. It would have intercepted the most material as it formed in a warm, dense molecular cloud. This shows the 1638 Dalton unit, where the center is a silicon atom, and that is at the vertex. Blue is oxygen, open circles are iron, with iron bounded to the antiparallel glycine chains. The lattice has a diamond 2H structure, but this only refers to the symmetry. In practice, it's almost empty. It has silicon atoms at each vertex and 5 nanometer connecting rods. Its density when empty is 0.03 grams per cubic centimeter. The amount of space the lattice fills can be measured by constructing tetrahedral shapes around each of the tetrahedral vertices. In the bottom right, D shows the truncated tetrahedron of Archimedes. From now on, I'll refer to it as TTA. All its edges are the same length. So if we use 6 TTAs positioned with the pattern of their spheres at the 6 tetrahedral vertices of one lattice hexagon on the left, the extended layer shows repeats. Gray triangles are empty small tetrahedrons. Dashed lines locate the position of the lattice hexagons viewed from above. And the point here is that 23/24ths, the TCAs fill 23/24ths of the lattice space. So here I'm going to refer to the scaled ratios of elements in hemoglycin to solar system abundances. While its space-filling efficiency, hemoglycin could have intercepted much material while in the protostellar molecular cloud, even potentially becoming a dominant component of dust, which prompts comparison with solar system abundances. We took the solar system abundances from the Anders Grevas 1989 table. We scaled the ratio of the elements to hemoglycin. So hemoglycin is H and the solar abundances are S. Suppose, for the sake of argument, nitrogen hemoglycin to nitrogen solar system is set to 1. All solar system nitrogen is bound in hemoglycin. Clearly, this is not the case. Then in the solar system, carbon and iron are only in slight surplus relative to hemoglycin. So the dominance of dust by hemoglycin is not inconsistent with solar system data. This is a cartoon showing how the lattice secretes the glycine that it's composed of, the iron, the hydroxyl groups, and the silicon. Now I want to just consider cosmic dust and reconsider cosmic dust. On the left, we have old dust properties, which is of a density of 1 gram per cubic centimeter. If the new dust has a large hemoglycin component, its density is 33 times less. The composition of old dust is graphite, olivine, magnetite, and then mantle organics, carbon monoxide, water, ammonia, and methane. The composition of the new dust could be hemoglycin. It will also have condensed matter internally in the volume of the lattice, which will be the same as the old dust, carbon monoxide, water, ammonia, and methane. The absorption of old dust is typically the UV bump at 216.5 nanometers, and they say it's due to graphite, which it will be. 6.2 due to the seed double bond oxygen, and 9.7 to silicate. If hemoglycin is taking part in dust, it will also show absorption of the UV bump, but at 220 nanometers, and that will be due to the iron and the glycine. 6.2 microns in the IR component will be amide 1, and 9 to 10 will be the silicate. The old dust has an extinction curve fitted by graphite spheres. In the new idea, we have shown that hemoglycin lattice with 7 rod directions radiates exactly like a uniform dielectric sphere. There's no new polarization effects. And to qualify that statement, an electromagnetic wave came into the lattice and induced polarizations, which were then re-radiated. The radiated electric field of each of the lattice rods was summed, and the resulting intensity was plotted as a function of the angle made to the propagation direction of the incoming radiation. The sine theta distribution was identical to that from a uniform dielectric sphere. This was a surprise because there were 7 different rod directions in the lattice. My conclusions are that hemoglycin is present in many solar system samples. It forms an extremely efficient lattice in terms of the space enclosed per molecular rod. Here the work has not proved that it is the most efficient of all regular lattices. However, we can state that as a component of dust in a molecular cloud, hemoglycin may be able to accrete more rapidly than any other topology. This characteristic will allow it to rise to dominance in a dust cloud, and if dominant, hemoglycin could, in principle, provide a large fraction of the material in our protocellular disk. Thank you.
Thank you, Julie, for a great talk. We have time for questions. Jake? Yes.
What are the photoelectric absorption properties of this dust? I mean, a large...
The range of...
So, for example, the pH is a...
Yeah,
pH
the range is from about 0.2 nanometers to 15 microns.
Right. No,
And it completely is the same almost in that range for PAHs, except the molecule behind the molecular components behind it are not the same.
Yeah, so if you shine FUV light on these, what are the photoelectric properties? I mean, in terms of ejecting photoelectrons.
Now,
Well,
you
I
help
can
physicists?
answer, excuse me, I can answer that's very similar to pHs, basically.
Any other questions for Julie? If not, let's thank Julie again.
All right. Hello, everybody. Hi, everyone. I'm Scott. I'm a postdoc here. And I usually work on galaxy simulations in the circumgalactic medium, but my PhD was on the Magellanic Clouds, and I'm talking about those today for old time's sake. So this work is following up some recent work done by Jesse Hahn, published a couple months ago, looking at the origin of hypervelocity stars to learn about the Large Magellanic Cloud. And so here is the plot showing, well, you can see the gist of it. This is showing the distribution on the sky of the hypervelocity stars detected in Warren Brown's survey from about 10 years ago. And each of these stars is a young, bright star moving faster than the escape velocity of the Milky Way out in the halo. So these are at 50 kiloparsecs away from us or so. And there's this conspicuous clump up here on the top right. And so what Jesse did was he used a combination of integrating the orbits of these stars as well as forward modeling the production of these hypervelocity stars to show that this clump mostly seems to come from the LMC. They don't come from the center of our own galaxy. They seem to point towards the LMC. And the formation mechanism that seems most plausible, that really only formation mechanism that seems plausible for these stars, is the Hill's mechanism, in which we have a binary star system that gets a little too close to a supermassive black hole. One of the stars gets captured, and the other star gets thrown out at the orbital velocity of the binary, which is typically thousands of kilometers per second. So these things are thrown away from supermassive black holes very, very fast and escape the galaxy. And so the detection of these hypervelocity stars originating from the LMC indicate that the LMC must have a supermassive black hole. So that was punchline number one from this first paper. And the follow-up work that we're doing now is to use the trajectories of these hypervelocity stars to figure out where this supermassive black hole was in earlier times. So we can track where the LMC was throughout its orbit as it's been approaching our galaxy. And so to do this, we integrated orbits of the LMC, shown as this little black dot in the line. That's the LMC's orbit for one particular set of initial conditions. And here's our Milky Way, an approximation of the location of its disk. And so we have disk and halo potentials for each of these galaxies that we then self-consistently integrate in time. And then we also throw in a whole bunch of hypervelocity stars. So we sample the uncertainties in the hypervelocity stars' position and velocities and track them in time in this evolving potential as well. And we look at how close do these hypervelocity stars get to this LMC. So this is showing the separation between the LMC and the hypervelocity stars as a function of time. Present day is on the right. And a whole bunch of these get actually pretty close. This horizontal line is 500 parsecs away from the center of the LMC. And so we can look at the distribution of closest approach of all these hypervelocity stars. And this little box is that 1 kiloparsec cube centered on the center of the LMC. And for this particular LMC orbit, 22 of these 1,000 samples go through this little box. So there's a few of them that seem to go right through the center of the LMC. And we can do this for a whole bunch of different orbits. This is another one in which the hypervelocity star doesn't get very close. None of them really get closer than 5 kiloparsecs. So therefore, this orbit is less likely, given the hypervelocity star observations, than this top orbit. And we quantify that likelihood based on the number of hypervelocity star orbits that pass within this little cube. And so this is a high likelihood orbit, this is a low likelihood orbit, and we sample a whole bunch of orbits of the LMC to see if we can see which ones are best. So here's our whole blob of LMC orbits. We've sampled the errors in distances and proper motions, and we've covered the whole face of the LMC. And we can then look at the likelihoods of all these different orbits. So each of these dots is one of these orbits on the face-on-sky projection of the LMC, and they're colored by their likelihood. How many of these hypervelocity star orbits get close? And this is looking just at one of the hypervelocity stars, HVS3, which has to come from the LMC due to its proximity. We can also explore the distribution in right ascension and distance and declination, and we see that it's not super clear in these plots, but we do see a strong stripe here on the on-sky distribution, which indicates that's where the trajectories happen to cross best. And so in the next few steps, we increase the number of samples to 10,000. We take 10,000 LMC orbits and 10,000 hypervelocity star orbits to fully sample the space. And this is just a likelihood. We want to actually know, well, where do we think this, the most likely center of the LMC is? So we apply a prior distribution. We think the center should be near the center. These X and plus, and you'll see those better on the next slide. But there's a few dots right here showing dynamical centers of the H1 and different stars. And so we think it should be close to here. So applying that prior, we get a blob that looks like this. And so this distribution shows where the present day position of this supermassive black hole should be. And so we can use different hypervelocity stars to test that. And these different stars are probing different times in the past. Because these hypervelocity stars have different trajectories, they're intersecting the orbit of the LMC at different times. And so this is getting HVS3 to are about 400 million years into the past. And combining all of these constraints together, we get an indication that the present day position of this supermassive black hole, based on where it must have been in the past, is a little bit 1 or 2 degrees above these other dynamical centers that I mentioned before. This is 3 different stellar tracers and then the H1 tracer. The other thing that we want to do is we want to say, well, where actually was the LMC at those earlier times? We don't want to only learn about where's the black hole today. We want to look at where was the LMC in the past. And so here's an edge-on projection. We're zoomed out into Cartesian coordinates now. This tiny little gray oval is the Milky Way. Here's the LMC at the present day. And it's the possibility of where it could have been in the past. The green line and the orange line show 2 orbits that have been used in full n-body simulations. This green line is an orbit from n-body simulation by Eugene Vasilyev, and the orange line is from Gertina Bezla's work using full hydrodynamics. And this red region, well, it's supposedly red, this wider region is the possible orbits only using the present day constraints. So we measure the dynamical center of the carbon stars, we measure their uncertainties in their position, their velocity and everything, and we integrate that whole spread backwards. We get any orbit is possible, basically. The second passage orbits that have already gone around the Milky Way once, and first passage orbits where the LMC is just approaching now for the first time, anything's possible. However, if we now require that it's got to actually get near hypervelocity star number 3, that gets narrowed a little bit. Still, we have both possibilities, but it is a smaller area. We can then use HVS7 and HVS15 as well. We get different constraints and put them all together. We get a much tighter constraint that actually, surprisingly, aligns very well with Eugene's orbit, at least the past 3 or 4 billion years of Eugene's orbit. And so here, I'll just throw up my conclusions here quickly. And the point that I want to make is the combined likelihoods and posteriors of these 3 hypervelocity stars line up very well with Eugene's orbit. And this is a second passage orbit. However, its first pericenter was 8 billion years ago at 100 kiloparsecs. So this dichotomy between first passage and second passage is still is a little bit subtle now, because we've ruled out orbits that are like circling around the Milky Way a zillion times. Those are not possible. However, if the LMC happened to glance by the Milky Way, a few billion years ago, that maybe isn't ruled out. And so we're following up on this with hydrodynamic simulations to see if constraints on the Magellanic Stream and the Magellanic Corona, the circumgalactic medium of the LMC, can illuminate some more of these details. We've also put in a proposal for HST time to get better constraints on the hypervelocity star properties, because if we can improve the proper motions of these hypervelocity stars, we get a much tighter constraint on where the LMC must have been in the past. So thanks, everybody.
Thank you, Scott, for a really fascinating talk. We have time for questions. Yes?
I'm wondering how you model the LMC and SMC system. Are these 2-point masses, or are they extended? Do they have internal degrees of freedom? And if yes, how does the internal degrees of freedom influence the overall orbital elements in the scale?
Yeah, that's a great question. So right now we are using fixed analytic potentials. However, they are radially extended. So it's a Hernquist profile with a mass and scale length that fit the previous observations. And we don't include the SMC in these models. However, we've run some tests, and it seems like the inclusion of the SMC doesn't alter the likelihoods and the posteriors of these orbits very much due to the very short time scale. However, it will change a lot, obviously the gas properties, and it could tweak the actual locations of the orbits a little bit.
Liam, please.
So I think one of the slides where you had a mole view projection that didn't quite render on the projector but was visible up there. Yeah. Exactly. Okay, so I'm guessing the shaded region up there is the footprint of...
That's right. So you should see a shading region right here. This is all shaded out. Wherever, basically, there's a few spots up here and down here. And then
Yeah. So my question is, when you fill in that region and you detect maybe 3 times more hypervelocity stars, how well can you do on the orbit?
That's a great question. So yeah, in Jesse's models, he's basically forward modeled the production of these hypervelocity stars, and you see a trail. All of these fast-moving LMC origin stars go all the way down from here to the LMC, which is down here. So we should have a whole bunch more that come from the LMC. And with, as you could see from, let's see, this guy, any given star, like these constraints are pretty good because they go back 400 million years, but any given star gives you okay constraints, but putting them together gets a quite tight constraint. So as we add more and more and more, I think that we'll get exponential payoffs there. The other thing is the longer ago in time we can look, the more constraints we'll get. So this is from 30 million years ago when HVS3 was ejected, and these are closer to 400 million years ago. So the stars in that shaded region are likely to be ejected less than 400 million years ago. So that will provide slightly not quite as strong constraints, but still the more stars, the better, I think.
It gives you the black hole, it doesn't...
Yeah, right. Yeah, so we'll be able to really narrow in on this plot here with more stars, for sure.
Yeah, you said that the present-day best fit location for the black hole is about 2 degrees north of the dynamical center.
Yeah, here.
Any interpretation how I got there, like tidal things with the
Yeah, so I mean, the LMC is a bit of a mess. It's been interacting with SMC for billions of years, and it's just passed at least one of its pericenters of the Milky Way. So there is a lot of forces going on there. There have been studies looking at the sort of wanderingness of black holes in dwarf galaxies, and a variety of effects can move that black hole around. Personally, I think 2 degrees is a bit bold. I think that it would be surprising to find it way up here. But we are looking, Jesse's looking for various sources and things that we could try to get more information on. Yeah, I think that it's not out of the realm of possibility that it's offset from these other dynamical centers. There's a full degree basically between the stellar center and the H1 center. So seeing a degree in a different direction for a different tracer is not crazy, I think.
Quick question, final, yes.
Very quick question. Can you also constrain the mass of your supermassive black hole that you need?
So yeah, Jesse did that in the first paper based on how many of these hypervelocity stars we're seeing. And so that, I think to Liam's point of finding more of these, will really hone in on that value. In terms of tracing their orbits back, I think that's less of a detail that we're really probing here.
All right, so let's thank Scott and all our speakers for today.